breakfast edition of calculus separable equations.
This bacon is really good.
Yeah, the food is delicious today.
Can't believe God made
Did you pass
himself
the
paid
bacon?
for it.
Thank you, Trina. Shout out to Trina.
Bev, no brought cookies.
And Jeff brought cookies. Yep. All right. So today, really the last day of notes, and then we're going to start reviewing for the AP test come Monday. So make sure everyone's responsible for that AP test packet. You really should have something down for every single question. If that's not there, then you're going to see Mr. Torres' wrath come Monday. All right. You've had a month to work on it. Okay. Anyway, so separable equations. A separable equation is a first order differential equation. Now, when I say first order, do you know what that means? Differential equations have derivatives, right? If it's a first order differential equation, it only has one derivative. It doesn't have a second derivative. It only has y and y prime in it. Nothing else. Right? Can't have y double prime. That's what first order is going to mean, a first order differential equation, in which dy dx, so that's the derivative of y with respect to x, can be set equal to a function involving x over a function involving y. So essentially, all your x terms are on top, and all your y terms are on bottom. So the reason that so essentially you want to be able to set dy d over dx equal to g of x, that's our function in terms of x, and h of y, that's a different function in terms of y. What that does is now you can take this and you can cross multiply. If you cross multiply, you end up with this equation over here on the right. And the general form of so the way we can solve separable equations is now we can differentiate both sides, really not differentiate, that should be integrated.
Wait, is it h of y, or h of y?
Yes, it is h of y, because that's a function in terms of y. All right, I'll show you what these problems look like in a second. Now we can integrate both sides, so that's going to be now we can take an integral from both sides, take an antiderivative, and if we take the antiderivative, we may then be able to solve for y. So sometimes when you do this, you're going to be able to solve for y, sometimes you won't. Again, show you what that means. So sometimes you're going to have kind of a function where you can say y equals, and it's going to be 3x plus 2y, or sorry, 3x plus 2, and you've got your answer. Other times, you're going to have something that kind of looks like an implicit differentiation problem with x and y in it, and you're not going to be able to solve for that. No big deal. All right, all set here? Okay, so solve the differential equation. How do I know this is a separable equation?
X on top, Y.
X is on top, y is on bottom. All right. The new equation I'm going to be able to create that does not have any fractions in it. How do I write this with no fractions? I know you've all got food in your mouth. Cross multiply. So we're going to say x squared dx is equal to y squared dy. And essentially, our goal is to try to solve for y. We want to know what the function is that solves for y. We want to know that value that is a possible solution to this differential equation. This function right here is another saying y prime is equal to x squared over y squared. That's a differential equation. That's exactly what we've been working on for the last three days. Okay, once you have it written like this, you can integrate or anti-differentiate both sides. Right. So here you're anti-differentiating with respect to x. On the right-hand side, you're anti-differentiating with respect to y. So when we anti-differentiate x squared, what do we get? Anti-differentiate x to the third over 3.
From where to where?
You're just doing it's a general form. It doesn't. You're not asked to find volume here, so that the actual boundaries don't matter. And on the right equals on the right hand side. anti-differentiate with no boundaries, we have to include one more thing, and I know AJ knows it. Plus C. Now, do I need to write it on both sides? No, because a constant here and a constant there can all be moved to one side. So we could turn this into this equation is solvable for y. So this is one of the cases where it is actually solvable for y. If I was to say subtract c to both sides, x cubed over 3 minus c equals y cubed over 3. I can still times 3 to both sides. I would end up, the 3's here would cancel. I'd be with x cubed. Still need to distribute minus 3c equals y cubed. And I could solve this by taking the cube root to both sides. And I could actually come up with the equation. Y does equal the cube root of x cubed. Now, I could write minus 3c and it's correct, but c is a constant, right? 3 times c is also going to be a constant. So all I need to write is minus some different value. And you don't even need to really say that k is equal to 3c. It doesn't really matter. There's some constant here. So what this means, if I substituted in this and its derivative into the original equation, right? So I would put the derivative on the left-hand side. X squared would be on the top. That's not going to change. If I took the bottom square, that cube root square, it would prove out to be a true solution. Does that make sense? We could prove that if we needed to, although I'm not going to ask us to do it today.
What was on the left side?
This is y prime. So if I took the derivative of this, so I would need to figure out y prime of this. It's a solution because if I found out what y prime was, you'd have to do chain rule, right? It'd be this to the negative 2/3 times 1/3 times x squared times 3x squared. You'd see that a number of, all this stuff is going to cancel out essentially. And actually, if you're really good, you start to see it a little bit. Like when you do the chain rule, do you see where the x squared is going to come from with the chain rule? Right? And if that's going to cancel out with the other side. You can see it on the derivative. But anyway, that's for another day. Okay, so let's stick with it. A little bit more challenging here. So separable equation, I think it's pretty straightforward that this is a separable equation. What are we going to do to both sides? Or what are we going to do to cross multiply? So 6x squared dx equals 2y plus cosine y dy. Good. Next step. Integrate both sides. So I anti-differentiate 6x squared. I get x cubed over, 2x cubed. 2x cubed. Yeah. Equals, over here, that's going to be y squared plus, antiderivative of cosine. Derivative of sine is cosine. So plus sine y. Now, plus c. What's that? Derivative of sine is cosine. Right? So when we take the derivative of this, it's going to get cosine. Right? It's tricky because I know we've gone from derivatives to antiderivatives and back and forth these last couple sections. Okay. Do you think this is one where we're going to be able to solve for y? No. Sometimes you're not going to be able to solve for y, and in that case, this is one where you have to maybe figure out some implicit differentiation. Although again, not something I'm going to ask us to do. You could maybe use implicit differentiation to find y prime, but we're not worried about that today because we actually don't have a way to solve for y. So, but this is your answer. That equation, if you could graph it.
How do you know you can't solve for y?
Try to get y by itself.
There's a sign.
Can you get y by itself? Yeah.
So if it's too much of pain, just don't do it.
Yeah, exactly. It's too much of a pain.
You know, it's not a little word. Wow.
Yeah, I know. Promoting this. emptiness. Okay, last one for today. Not trying to be tricky here, but there's like a small trick at the very beginning. What do you think I mean by that?
dy over dx is the same.
Yeah, y prime is the same as dy over dx.
You got it.
Did I get? And so this is also not a fraction. How could I make that into a fraction?
Y to the negative 1.
Y to the negative 1. So over y to the negative 1. Yes. All right. What's that? The moving of the. All right, where are we gonna go from here?
X squared dx equals y to the negative 1.
I get x squared dx equals y to the negative 1 dy. Looks good.
Ln of y.
Yeah, so in that differentiate, and this becomes x cubed over 3 equals, what do we say here? ln, absolute value of y. That's the technical formula, and then the plus c.
Yeah.
Plus c. This one, yeah, you could actually solve for, yeah, you could solve this one for e, or you could solve this one for y, and the way you do it is essentially you e to the x cubed over 3. In fact, you know what the easier way to do this is, instead of writing plus c here, I'll write plus c here. So that becomes e to the x cubed over 3 plus c equals e to the ln of the absolute value of y. And what happens with the e and the absolute value of, the e and the ln, sorry. The e and the ln cancel out, and now you have something that says the absolute value of y is equal to e to the x cubed over 3 plus some constant.
Is it wrong if you don't have the absolute value?
I mean, it's very nitpicky. Alright, that's like a bare basics on separable equations. It's, briefly mentioned on the syllabus, so if you did see it, again, I don't think, like I told you, differential equations is really the second part of calculus. When you get to calculus B, C, and beyond, that's where you start seeing this way more. But if you did see it on the AP test, that's the only reason we spent a little bit of time on it. Any questions?
Bye, Nitschke.
Enjoy your rest of your trip.
No.